I was up in the air about whether or not to do a screencast on Chapter 11, but then I said, this will be a lot of fun. It'll be a gas. So I think I'll go for it. In any case, pardon the dad jokes or the teacher jokes, they're pretty much similar. A little preview of our chapter. One of the reasons why we want to understand gases is because of our atmosphere. And one of the reasons we want to understand our atmosphere is for all the times we climb mountains. Oftentimes people say, well, why do you want to climb a mountain? And the saying from a mountain climber over a century ago who was going to ascend Mount Everest, his answer was, because it's there. And of course, part of exploring our planet and exploring beyond our planet is because we are curious people. That is a characteristic that God created in us, this innate desire to study and investigate his creation. Of course, the tragedy is always when we study creation without recognizing the creator behind it. Romans 1, of course, reminds us about that. Everything we learn in science should direct our attention to the God who made science possible. Because that God made creation rational, he made you and me rational, and that's the only way you can do science, is a rational universe that follows patterns and regularities that can be described by laws in the language of mathematics, and then human beings made in the image of a rational God who can begin to discern God's genius in creation. So, people that climb mountains can sometimes get acute mountain sickness, right down here. I've only experienced a little bit of this. My youngest son going up Mount Adams one time, which is a dormant volcano in Washington State, they kind of did too much too soon without necessarily maybe being in the proper condition or acclimated, and they really got kind of giddy when they were up there. And of course, when you're giddy and not thinking straight, that can be very dangerous. And part of that giddiness is because as you go higher and higher, the concentration of oxygen at that altitude becomes less and less, and you begin to suffer from hypoxia. The concentration of the Earth's atmosphere is 21%, and of course all air is going to be 21% oxygen, except that as you get higher and higher, the pressure drops because the air gets thinner and thinner. So even though you still have 21% oxygen, if the air is thinner, each gulp of air that you breathe has less oxygen than a gulp of air at a lower altitude, and you're not getting as much oxygen. You can see from this chart right here that as you get higher and higher, and as your pressure of the atmosphere gets lower and lower, the percentage of oxygen in the air drops all the way down to 72% based upon the partial pressure of oxygen at that particular altitude. So the partial pressure is the pressure of a particular gas that's in a mixture of gases. And there's more about this later in the chapter. One last comment is that red blood cells, when they transport oxygen from your lungs to all the other parts of your body, there are about 80% saturated. And when you get less and less of that, then the cells in your body are not getting sufficient oxygen, and it has negative health consequences, as you might imagine. Now, there's lots of other reasons for studying gases, practical ones like hot air balloons, which are both interesting and fun, but also can carry weather instrumentation, surveillance instrumentation, up into the atmosphere, scientific measurement instrumentation. Going down into the water, you got to figure out a different way in order to get your oxygen. So you go up into the atmosphere, you go down into the water. We have this very practical device of rapidly inflating a polymer to absorb your impact in an automobile accident or crash. We have an entire chapter devoted just to gases, and one of the reasons is because, well, compared to liquids and solids, gases are very easy to study. They're very easy to model, and that helps us to understand gases. In a later chapter, chapter 12, we're going to get to liquids and solids, and those are much more complicated and difficult to understand. In fact, in physics, we have an entire chapter based on fluids, which can be moving air, but also moving liquids, such as water. And that's very complicated, and of course solids are complicated, particularly understanding crystalline structure, but that's in a chapter yet to come. So when we talk about studying gases, number one, a lot of your common elements and compounds, such as oxygen, nitrogen, and methane, are in the gaseous state at standard temperature, at room temperature and pressure, or standard temperature and pressure, sometimes called STP, standard temperature and pressure. More about that later. Obviously, we want to study gases because of our atmosphere. And atmosphere, we talk about how energy is transferred, and it's one way in which energy is transferred from place to place, as well as material can be transferred from place to place, the stuff that's in our atmosphere, the solids in the atmosphere, as a result of the air currents. And of course, we have air currents because of the uneven heating of the surface of the planet, the tilt of the planet relative to the sun at a 23.5 degree angle, which is primarily responsible for our seasons, which is a huge part of the uneven heating of the surface of the planet during the course of a year. We certainly want to get oxygen distributed all over the planet from its primary source, which would be the phytoplankton in the ocean doing photosynthesis. So we got to have those life-sustaining chemicals. Also in our conversations and scrutiny of changes in weather, which is a subset of changes in the overall climate. And we know from looking at proxies such as ice cores in glaciers and in polar ice caps that the planet's surface and the temperatures and weather conditions on the planet have changed and fluctuated over many thousands of years. And of course, when we talk about global warming, that needs to enter into the discussion. I remember in the 1970s having just moved to St. Louis and taking a graduate course in energy at Maryville University. The concern was not over global warming, but over global cooling due to pollution blocking the light coming in from the sun. And then there were concerns of the planet entering a new ice age prematurely rather than in its normal cycles because of human pollution. And then that gave way, when it wasn't materializing, to global warming. And then the overall temperature of the planet sort of plateaued, I don't know, for about 17 years. And then the conversation became all about extreme weather events, EWEs. And then that didn't materialize either in terms of the statistics of hurricanes and tornadoes. And then it just became climate change overall. And do human beings play a role in climate change? Of course we do. God's intention is for us to have an impact on the planet. He's designed this planet for us to be here. But then, of course, in our fallenness and brokenness, we can also do negative things to our planet as well. And we always want to be involved in the redemptive process of combating the negative consequences of unnecessary and extreme water pollution, air pollution, land pollution. So this is a conversation that Christians should always be engaged in, and recognizing God's sovereignty over his creation on one hand, but also man's responsibility and stewardship coming out of Genesis chapter 1 that we are supposed to play. Whether or not carbon dioxide is significant is another conversation. It's a subset of talking about climate change. And that, and when we talk about carbon dioxide, it's a natural gas that animals and humans put into the air, but its primary function, carbon dioxide, is as plant food, the essential ingredient or reactant in photosynthesis. And there's an ongoing question. Oceans capture carbon dioxide, and if during the times when the planet is warming very gradually by a degree or so, maybe over a century, is that because of carbon dioxide as a greenhouse gas already in the air, or does the carbon dioxide in the increases in carbon dioxide in the air result from the degassing of oceans as they get a little bit warmer in their natural fluctuations when they're absorbing solar energy? Just like a can of soda, when it's opened and the temperature goes up, loses its carbon dioxide, its fizz. So there's all kinds of questions here that need to be considered and held in balance. All right, another point is that studying gases is really simple because we can consider in our models gases as being independent individual particles pretty far apart from each other relative to liquids and solids, and therefore we can pretty much ignore the intermolecular forces when these particles get close to each other. But that's something at the very end of the chapter we consider. What happens when our ideal gases, and we'll talk about the ideal gas in a few minutes, what happens when our ideal gas is no longer ideal because of extreme pressures at either end or extreme temperatures. Because in those conditions, then you have to think about intermolecular forces, and you have to think about the particles themselves occupying volume, occupying space. When the gases are far apart, the amount of space the particles of a gas occupy compared to the overall volume is pretty minimal, and we ignore it. Finally, we have two vocabulary words that pop up in science a lot: qualitative and quantitative. Qualitative would be descriptive. You're not actually taking measurements or gathering numbers, but you are making observations with your senses and your instrumentation. Then quantitatively is when you are using your instrumentation and actually making measurements. So there's a big difference there between a qualitative and quantitative study. Some of your labs are qualitative, most of your labs are quantitative, where you make measurements and do calculations. Someday, if you do a master's or a PhD dissertation, you might choose a qualitative versus a quantitative one. My doctoral PhD was primarily qualitative in that I interviewed 32 practicing scientists and asked them, what experiences did you have growing up through high school that enabled you to persist in this very difficult endeavor of getting a degree and eventually a job in the area of science? There was a little bit of quantitative, but most of it was qualitative. So a little bit about airbags as long as we see this picture. In an airbag, you need to fill this bag up faster than it takes for your head to go forward and potentially collide with the steering column or the dashboard. And so the typical automobile collision takes place in about 1/8 of a second. So you need to have your airbag filled or inflated in less time than that. And so this is about, looks like about 5 times faster. And the way you produce that gas instantaneously is through an explosive decomposition. And you want that explosion to inflate the bag without causing the bag to rupture or without causing any of the pieces of plastic and so forth that are in front of the bag before it deploys, so you don't actually see the bag until it's necessary. You don't want those pieces to damage the person's face. And of course, there's an ongoing lawsuit over the last several years of a particular company located in Japan, I believe, that mass-produced airbags and there was a problem with some of those airbags when they exploded open, actually damaging people's faces. In any case, we often decompose compound like this, sodium azide. That AZIDE is that nitrogen part. And of course, if you think about nitrogen gas likes to have a triple bond, which makes it extraordinarily stable. So when you have a compound like sodium azide, that's relatively unstable. And to go from 3 nitrogens connected to your sodium to producing nitrogen gas, that reaction will go to the right very, very rapidly as you increase in stability. Next, another nice thing about studying gases is basically you need to know 4 quantities. And we'll talk about them interchangeably. Back and forth: pressure, volume, temperature, and the amount of gas, which we call the mole. We'll talk about them. Well, let's talk about gas pressure for a few minutes. Pressure can be measured in a barometer. Here is a very early barometer over here on the left. One of the earliest people to begin to study gases is Evangelista Torricelli. No, there is not a pasta that is named after him. He was not the second cousin once removed to Bill Ravioli or Susan Mostaccioli. In any case, this is all the way back to the early part of the 17th century, and he developed this thing called a barometer. Baro is an old-fashioned word that refers to pressure. So this is a meter for measuring pressure. And he took a long test tube of glass open at the top, and then he filled it to the top with mercury, and then he turned it upside down and inserted it into a basin of mercury. And of course, some of that mercury under its own weight would move downward and then stop. And you'd have a vacuum up here at the top. And the atmospheric pressure as it pushes down, when you study pressure in physics, you know that the pressure on a fluid gets distributed in all 3 dimensions of that fluid. And in this case, it's going to push up here, just like it's pushing on the sides of the container, and pushing down. And when the force pushing up is equal to the weight of the mercury pushing down, you reach an equilibrium at a certain height. And as the atmospheric pressure goes up or goes down, this column of mercury is either going to go up or it's going to go down. So all you have to do is calibrate the side, put some numbers there, and you can watch the level of mercury go up or go down. When you have a high pressure system in the atmosphere, which is where the air from high up is pushing down on you, it's going to make the mercury go higher. And the barometer is going to go up, we say. And then when you have a low pressure move into the area, and that's where the air is actually rising off the surface of the earth. So it produces a low pressure. Water vapor, of course, in a low pressure, as it rises, will begin to condense, and you're going to get clouds. And low pressures are associated with rain and snow. High pressure with clear skies. But when you have a low pressure, the barometer reading goes down. And so this is a way of measuring changes in pressure. You can also hook it up to a container of gas to measure the pressure of the gas. Now, we have lots of different ways of measuring pressure. We can begin by measuring pressure in terms of millimeters of mercury. If these calibrations here, back on the left, are in millimeters, we can measure it going up and down. We can also say, well, what is the average barometric pressure? How many millimeters of mercury will be supported in a column like this at sea level on average all over the planet? And the answer is about 760 millimeters of mercury, which is about 3/4 of a meter. Think of a yardstick being a little bit shorter than a meter. A meter is 39.37 inches. So, and a yard, of course, is 36 inches. And we call that our standard atmosphere, or 1 ATM. And we're not talking about those devices where you get money out of automatically at the bank, an automatic teller machine. This is a different term. ATM is short for an atmosphere. So one standard atmosphere, then, we say is defined as 760 millimeters of mercury. So 760 has an infinite number of significant digits in this definition. However, that's not a metric unit. Our metric, System International, our metric unit is called the Pascal because it's measured in newtons per meter squared. So we wonder how many pascals are there in an atmosphere? Well, a newton of force, and maybe we could say, newton of force is kind of like if a very small bug, like a mosquito, landed on you. That a newton of force is not an awful lot. I think I'm remembering that correctly. And so a pascal, which is a newton per meter squared, is also a very small unit. And so how many pascals are there in in one atmosphere? And we're going to measure it in kilopascals to make it a little more convenient. And the answer is about 100 kilopascals right here. 101.325 kilopascals in 760 millimeters of mercury in one atmosphere. A lot of times you will see this number here, 1.013 times 10 to the fifth pascals, and that is air pressure. And that little zero there is often a reference to air pressure, the kinds of pressure that's more or less right on top of you right now. We also measure pressure in bars, another short for barometer or barometric pressure, and that's defined as exactly 1 times 10 to the fifth. So you can see a bar and is the same thing as a 100,000 pascals. And so when we talk about millimeters of mercury and bars, there's a slight difference between them. And I'm not going to take any time to show you how to convert from one to the other. Dimensional analysis is where it's at to make sure you're multiplying or dividing correctly. Make sure you pay attention to your significant digits as well. So it should be pay attention to dimensional analysis. Sorry about that, keep you awake. Here's a little bit more about gas pressure. Let's say we want to measure the gas pressure in a container of gas. So we have a container of gas right here, and we take it in through this inlet, and then we close the valve, and now this pressure is going to be pushing down here at the same time that and as it pushes down, it's going to push this mercury up. And when you reach an equilibrium, you measure the difference in height in millimeters of mercury, and then you can convert that into pascals or any other unit of pressure you want. By the way, a millimeter of mercury is sometimes called a torr, named after Evangelista Torricelli. If we were to convert this to the English system, 1 atmosphere is about 14.7 pounds per square inch. So if you were to take the air sitting on top of you as it stretches as you go out into outer space, imagine this column of air that is on top of you, on top of your shoulders and on top of your head, and it fades away into outer space. And imagine you could capture all that air and put it on a scale and mass it out and divide it by the surface area of your shoulders and your head in inches, you would get 14.7 pounds per square inch. That's the atmospheric pressure. Now, if we were not using mercury, which is this nice dense liquid, and using water, because water is not nearly as dense as mercury. Mercury is 13.6 times denser than water. You would need a water barometer 13.6 times higher than a mercury barometer. A mercury barometer, if you're using a capillary tube of sorts, like we're using here, a mercury barometer would be able to mount on the wall of your house, for example. However, a water barometer would probably have to start off in the basement, and then you would read the value up there in the attic. So let's begin by talking about Boyle's law. And of course, Boyle is sometimes considered the father of chemistry. Boyle was born almost 20 years after Evangelista Torricelli. So he's very much in the second half of the 17th century. And the father of chemistry, a very, very devout Christian man. The quotes that we have from him in his writing, both in his scientific writing and in his own personal writing, very, very much a godly man, God-fearing man, a God who recognized that what he was doing was investigating in a systematic way God's creation, and he gave God the glory for all of that. And he's the one who first articulated well the fact that when we talk about pressure and volume, and we keep the temperature constant, they are inversely proportional to each other. Volume is inversely proportional to pressure. And then we can formulate that into a law. I think I'll do it right here. This would mean, therefore, that my volume equals some constant times pressure. So we could say that at one pressure, P1, we have a volume. And then we could say, well, at some new pressure, at pressure 2, we're going to get a new volume. And if we hold everything else constant, and therefore we can say that this equation becomes K equals V1 P1, and this equation becomes K equals V2 P2, and using the transitive property of quality, that if A equals B and B equals C, therefore A and C equal each other, we get V1 P1 equals V2 P2, and then what we can do is divide and get V1 over V2 equals P2 over P1. And there we have a way of using Boyle's law to calculate the new pressure if the volume changes, or the new volume of a gas if the pressure changes. Now, in this particular graph right here, what if we make some readings and we measure the volume of a certain amount of gas at different pressures? And let's say we create 5 data points. When we in these data points, the way that we're measuring the pressure could be by putting mass on a scale. If you look over here, we're weighing, the pressure is related to how much mass is in this beaker pushing down on the syringe and compressing the gas. You might see that my gas here is greater than the amount there. And then we record the volume that we get here. Now, when we go to make a graph and we put the mass, which is our proxy for measuring pressure, and we take the reciprocal of the volume, notice we get a line that can be described by y equals mx plus b. And this becomes a way of showing the relationship between volume and pressure. And of course, we can extrapolate on down and see where this is going to go. Of course, you can have less than zero pressure. And we'll look at another graph in a little bit and see what that tells us. And so here's our relationship. One thing that you have to remember is your temperature must be in Kelvin. The reason, of course, is if you left it in Celsius, and let's say we had I guess the temperature being in Kelvin, comes a little bit later. So hold on to that thought. So pressure is proportional to volume. You can't have zero volume. You can't have less than zero volume, and you can't have less than zero pressure. Of course, you can't even have zero volume because the particles of gas making up the substance, obviously, have their own volume. And here's one way of articulating Boyle's law, which I showed you before. And I'll let you do this problem right here. It's just a plug and chug problem. The effective temperature. Now here's where your temperature has to be in Kelvin, and you'll see why in a little bit. But he saw that that in Charles' law, Jacques Charles is late 18th, early 19th century, French guy, very interesting guy. He was a balloonist, and he flew balloons, and there's some fascinating stories about him. Anyway, he was the one that saw that volume and temperature are proportional to each other. So when we talk about volume and temperature, we know that the volume is proportional to the temperature. So therefore, we can say volume is going to equal some constant times temperature. Now again, temperature has to be in Kelvin, because if you had Celsius, you'd have negative volumes, and if you negative temperatures. And if you had negative temperatures, you're going to get negative volumes, which are nonsensical. So if we have at one temperature, if we have one volume, and then at a different temperature, T2, we have a different volume, V2. We solve these equations for K. So K is going to equal V1 over T1. And over here, K is going to equal V2 over T2. And then what we're going to do is set, well, if A equals B, if A equals B and B equals C, then that means V1 over T1 equals V2 over T2, and then we can multiply and have V1 times T2 equals V2 times T1. This is a way of talking about Charles' law. And of course, you can get super cold temperatures like with liquid nitrogen. You can take all of these balloons with their big volume and you put them in the liquid nitrogen, and it's so cold that the volume goes way, way down, and you can put 10, 20 different balloons into a Dewar flask of liquid nitrogen. And then when you take them out, they reinflate as the temperature goes up. And here's where if we make a graph of our temperature versus volume, and notice we're Celsius here to show these negative values, that we extrapolate a certain temperature at which the volume is going to go to zero. Here would be your zero volume. And that temperature, when we extrapolate, is a negative 273.15. You should memorize that number, negative 273.15. You should also have the number of 760 being 1 atmosphere memorized as well, because it's so common. Now, this Kelvin scale is very valuable, and we've talked about the different temperature scales way long time ago in the opening month of chemistry. William Thomson, an Englishman, who later was knighted and became Lord Kelvin, another very devout Christian man that you can tell by his writing, both his scientific writing and his personal correspondence. And he died a little more than a century ago, gave us this Kelvin scale, and was able to, or at least helped us to use this Kelvin scale, and came up with this idea of negative 273.15 as a temperature at which you basically have no translational motion of your particles at all, because remember, temperature is a measure of the average kinetic energy, and when the velocity goes to zero, then you're at your absolute temperature. Of course, there is a quantum effect. There is kind of a quantum vibration going on even at absolute zero. So this is Charles' law. It always has to be expressed in Kelvin, and I will let you do the calculation on Charles' law with this simple problem on your own at some point. Now, we can combine Charles' law and Boyle's law and put them both together and be able to consider all three variables, pressure, volume, and temperature. This is sometimes called the general gas law and the combined gas law. Now, in a little bit, we begin to talk about, well, what is the effect of adding or taking gas away from the volume of a container? In other words, the volume is going to be proportional to the number of moles. And so we can also put in here the letter N for the number of moles. PV over NT equals PV over NT. And I like that one a little bit better. But of course, in most situations, 99.9% of the problems that you do and the research that you do, the quantity of your gas is going to be a constant, which means the number of moles is going to cancel out, and you're back to PV over T1 equals PV over T2. And I'll let you plug those numbers in. By the way, notice that it doesn't matter what units you use for pressure, as long as they're the same, because the units are going to cancel out. Temperatures have to be in Kelvin. It doesn't matter what units you use for volume, as long as your volume units are constant. If you're trying to find volume, whatever units for volume you put in, that will be the units of volume that you get out. So again, you need to be dimensionally consistent. Avogadro's hypothesis basically looks at the fact that it looks like gases combine in whole number ratios, which implies that atoms and particles and molecules and ions combine in whole number ratios. And that from him, of course, we get our Avogadro's number, 6.022 times 10 to the 23rd, as being the number of particles in what we call 1 mole. Now, another French and Italians are big in this. Joseph Gay-Lussac, way back in the first half of the 18th century primarily, 19th century, that equal volumes of gases under the same conditions of temperature and pressure have equal number of particles. And coming over here, that's called Avogadro's hypothesis, that your volume is going to be proportional to the number of moles. And I'll let you do this math problem as well. Keep in mind that the ratio of my gases up here, if all my gases are in liters, I have a 1 to 3 to 2 ratio in this equation. And this is true for both volume and for moles. In the next screencast, when we talk about stoichiometry, you'll see we don't have to convert our volume of gases into moles because that's not going to change. And again, we can find our theoretical and compare it to our actual and find our percentage error. And this is some interesting storytelling about Jacques Charles. But first, back to Robert Boyle, who set the stage for Isaac Newton, another very devout Christian man who did wrestle with some significant doctrines. He wrestled with the doctrine of Trinity, which of course nobody can fully understand because none of us have the kind of minds, because of our finiteness and fallenness, that can fully grasp God the Creator, the Lord God Himself. Boyle did lots of other things, especially in chemistry, the father of chemistry. Jacques Charles was a balloonist. And interesting stories. The very first balloon trip, he captured hydrogen gas in a very, very large silk bag, which he covered with rubber so that the gas would not leak out of through the pores of the silk being a natural polymer. And he took a whole lot of iron, 450 kilograms, and a whole lot of sulfuric acid, and captured enough gas in that container to go aloft for 45 minutes. And he traveled 15 miles. And then when he finally had to land in the middle of a town, and the villagers were terrified. They'd never seen a person flying before, much less a balloon, and they tore this thing to shreds, thinking it was demonic or something. Later on, he actually got up to an altitude of about 2 miles. Imagine going up over 10,000 feet in the air, barely visible. And the story goes, and I think it was with Charles, but it might have been another French balloonist, was trying to beat the high altitude record, and he kept throwing stuff overboard from his basket. And at one point, he took an old wooden chair and threw that out of the basket. It happened to land in the middle of a village, and the villagers all of a sudden, in the middle of the village, this old wooden chair comes crashing down, and they couldn't see anything where it came from, and they figured, well, God must have some pretty shabby furniture. And it reminds me of a very classic, funny movie made in 1980 called The Gods Must Be Crazy, about an airplane flying over a village in a savanna region in Africa, and the pilot throws a Coke bottle out the window, and it lands in the middle of the village, and the villagers figured, well, it had to come from one of the gods, so it becomes an icon of worship. Now, the ideal gas law is when we put all of this stuff together, PV equals nerd. When we recognize that my volume is proportional to temperature, my volume is inversely proportional to pressure, my volume is proportional to quantity of the gas. Therefore, we can say that my volume is going to be proportional to NT over P, and then we throw in our constant. Let's call the constant R. And then multiply both sides by P, we get this, PV equals nert. And of course, the value of my proportionality constant R depends upon what my units are. And there are many, there must be 20 different values of R depending upon what units the researcher chooses to use for measuring pressure and volume in particular. PV equals nerd. So here's another number you should measure. It turns out that the volume of 1 mole of gas at standard pressure of 1 atmosphere and 1 Kelvin is 22.4 liters. And that gives us this constant right here. You have a more common constant than this one. This is the one that I use primarily for maybe my first 30-some years of teaching, but more and more when we shifted to the metric system in pascals, we use the Pascal equivalent instead of this unit. And those constants would be given to you on a test. And so here's a problem where you just solve for n to find your number of moles. And we're going to stop right there, and we'll begin to apply PV equals nert in the next screencast.